Hi, this is Stu Schwartz from MasterMathMentor.com. This is video AB, not essential, 24b. The topic is Newton's method, and it covers the AB manual, page 261. Shown is the graph y equals f of x. Back in your pre-calculus days, you learned techniques to solve the equation f of x is equal to 0. However, the method was dependent on f of x being factorable. If not, you had to graph the function and find zeros of the function, and your answer usually was irrational. The question is, how does your calculator compute the zeros? The method we're about to learn is called Newton's method, sometimes called the Newton-Raphson method. Newton was Sir Isaac Newton, 1642 to 1727. Newton's method is called an iterative process. Each repetition of the process is called an iteration, and the result of one iteration is used as the starting point for the next. In Newton's method, we want to approximate the solution to f of x equals 0. So we start with an initial approximation, or guess, and we call it x0. In the figure, it is clear that x0 is not a good approximation of the root of f of x. We then find the tangent line to f at x0. This line is y equals f of x0 plus f prime of x0 times the quantity x minus x0. We next find where this tangent line crosses the x-axis. We call it x1. We see on the graph that x1 is a better approximation to the root of f of x than x0. How do we find x1? We know its coordinates are x1, 0, so we plug this point into the tangent line equation that we just showed. Using the point x1, 0, we get 0 equals f of x0 plus f prime of x0 times the quantity x1 minus x sub 0. Therefore, x1 minus x sub 0 is equal to negative f of x0 over f prime of x0, and therefore x1 is equal to x0 minus f of x0 over f prime of x0. So now we can find a new approximation, provided that the derivative isn't 0 at the original approximation. We now repeat the process. We draw the tangent line to f at x1 and determine its root, calling it x2. This is now obviously a much better approximation of the root of f, and its formula is x2 is equal to x1 minus f of x1 over f prime of x1. We can continue the iterative process as many times as we wish. So Newton's method states that if x sub n is an approximation for f of x equals 0, and if f prime of x sub n is not 0, then our next approximation is x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. Let's show how Newton's method works for f of x equals x squared minus 2, with our initial guess of x0 equals 1. Now we know that the solution to this equation, when x is positive, is the square root of 2. Let's see how good Newton's method is. The best way of doing this is setting up a table with our columns x sub n, f of x sub n, f prime of x sub n, and f of x sub n over f prime of x sub n. We start with x sub n equals 1, and we know that f of x sub n is 1 minus 2, which is negative 1. And we can see this on the graph on the right. F prime of x is 2x. So f prime of x sub n is 2x sub n, and therefore when x sub n equals 1, we get 2. Therefore, we then look at the fraction f of x sub n over f prime of x sub n, and that gives us negative 1/2. So our new value of x sub n is 1 minus negative 1/2, which is 3/2. We start the process over again, and we then find f of x sub n, which is 3/2 squared minus 2, which is 1/4. F prime of x sub n is 2 times x sub n, which is 3. And f of x sub n over f prime of x sub n is 1/12. So our new x sub n is equal to 17 divided by 12. Usually these problems get messy in terms of fractions, so we will stop at that point. How good Newton's method is in approximating roots is dependent on how many steps of the process are necessary to get a result accurate to as many decimal places as needed. We show an Excel spreadsheet with n and x sub n in yellow, and the difference between our Newton's method result and the true solution square root of 2 in green. Note that with an initial guess of x is equal to 1, only 5 steps of Newton's method were necessary for our result to be as accurate as the tolerance of Excel, 15 decimal places. But that was with an initial guess of 1. Suppose your original guess isn't as good. For instance, suppose it was 10. Surprisingly, it only takes 7 steps to get our accuracy to 15 decimal places. And if we used an initial guess of 1,000, a ridiculous guess, it still only takes 13 steps of Newton's method to get our result accurate to 15 decimal places. So no matter what the initial guess is, Newton's method is very efficient, and the process is programmed into calculators. That is why when you ask a calculator for a root, you must make an initial guess. In problems 2 and 3, we are interested in using Newton's method to find the root accurate to 2 decimal places. You are given a function and a starting guess. In number 2, we are given the function f of x equals x cubed minus x squared minus 3x minus 2, and our starting guess, x0, is 2. We start the process and we go through the iterative steps. The question is, how far do we have to go? We go until we see no difference in our x values accurate to 2 decimal places. This will happen when our error f of x divided by f prime of x is equal to 0. So we can see as we go through our process that it is first equal to 0 when our third value of n, and therefore the value of x, which is our root, is 2.51. In number 3, our function is f of x equals e to the x plus x minus 2, and our starting guess, x sub 0, is equal to 0. We see that it only requires 3 values of n before we get to the root 0.44. Obviously, there are more decimal places. However, 2 decimal place accuracy, our answer is 0.44. In number 4, the function is y equals sine of x minus 2 cosine of x, and we want the smallest positive root. We know this function will have an infinite number of roots. We could graph it, but that would defeat the purpose of using Newton's method. It is a good idea then to make the initial guess equal to 0. However, doing so will find the root closest to 0, and it's possible that might be negative. You would then have to up your guess to 0.1, for example, and try it again. It could take multiple tries to get the first positive root. Luckily, we get positive values for x when the initial guess is 0, and the root to 2 decimal places is 1.11. Notice in the 2 previous problems, once we did our first step of Newton's method, our answer decreased to the root. In this one, note the oscillation of our Newton's method results about 1.11. This typically happens with trig functions.